Okay, so let's go over this quiz, okay, and see how you did. A few people were out, but hopefully they'll be listening to this, and we'll see what questions we pull from those lecture notes where I did, and I get that there was other stuff, but okay, what exactly does MRI stand for? It stands for what?
Magnetic resonance imaging.
Yes, magnetic resonance imaging. What determines the atomic number of an atom?
The number of protons.
The number of protons, period. The number of protons, right? Where are protons found? That wasn't on here. Where are they found? So what is the electrical charge for each of the respective subatomic particles? Neutrons have, where are they found? Right? Protons have a positive charge, and they're found in the nucleus, you said, and electrons have a negative charge. Right. What is being referred to when discussing valence electrons? What did the number of electrons in that outermost orbit, right? Right. Okay. Define ion. You said that it is an atom that has either taken on or given up valence electrons. Or maybe you said it's an atom that's charged, and that's fine too. Okay? Relax. Okay, there's several ways you could have said it, but okay, so I'll see what you said. But it should have been one of those. What is another name that we use for ion? Salts or electrolytes. That's exactly right. Those are other names. What subatomic particle determines whether an atom is an isotope of an element or not? Neutrons. The number of neutrons. Right, an unusual number of neutrons. Name the 3 chemical bonds discussed in class. We discussed ionic bonds, covalent bonds, and hydrogen bonds, did we? And then the next question said, what special type of chemical bond holds one water molecule together? H2O. What is that? It is a covalent bond, but and I'm going to give you credit. I'm going to give you credit, but what I wanted was the special type, and it's a polar covalent bond. And you're going to get credit for covalent, but you need to understand that water molecule being polarly covalent is why it acts the way it does with other water molecules. What's the weakest of all chemical bonds, but the most important physiologically, because it does hold water molecules together, and it holds your DNA strands together, and it holds your proteins in the shape that they have, and it's called a what? Hydrogen bond. That's exactly right. Who's given credit and the Nobel Prize for their work with radioisotopes and understanding how energy given off can be used in treatment and diagnosis?
Marie Curie.
It's Madame Curie, Marie Curie, right? Marie Curie. And then explain why atoms act the way they do. Who wants to tell me what you put? What you put,
I
Aaron?
put that structure dictates function. I don't know.
Well, structure does dictate function. And in this case, the answer to that question, that bonus question, would be to complete their valence orbits. You know, because their valence orbits, that structure, their valence orbits aren't complete. They'll play or not, but that wasn't quite specific enough. Okay, so you would have needed to say to complete their valence orbits. Isn't that right? And then you said something else. Did everybody think it was a second bonus? I hope so. Okay. So were these fair questions from the lecture the other day? Okay, I hope you thought that they were fair. I want to let you know that before we get too much further, if you're struggling with these 2 quizzes that we've had so far, that's fine. As I said, it's not hurting you yet, but it will start soon. So what you need to do is, if you're struggling and you're not getting notes well, and you're trying to re-listen to the recording and take notes with that, you're using your peers, because you have some amazing peers. You're doing everything else you can think of. We have tutors as well. So the learning, it's called, they just changed their name. The Learning Community, I want to say, TLC. Anyway, we have tutors that are free. So you can go in and try to sign up for tutoring services. And tutors don't teach you, but they can give you some hints about what you might be doing or not doing, or things that you could try. And And so what I have found, though, is that students, because of their through 12 indoctrination, they think that tutors, they just need to go sit and a tutor, somehow that's going to work. And it's not. It's the only way we learn is by being an active participant in our learning and doing what we need to do to get that information in. So anyway, but we do have tutors. So please, if you think that's going to be needed, don't wait until you've dug yourself a hole. Okay? All right. So, good morning. Thanks for being here. Here we go. Continued study of chemistry. And thank you, Ashley, Andrea, who one of y'all told me that we're going to talk about free radicals. What's a free radical? What is a free radical? What's a free radical? Anybody know? What'd you say?
It's bad.
Okay, that's good. So you know it has something that you don't want. You don't want free radicals, right? So you know it's kind of bad. And that's really true, and I have no idea where I am in the notes, but I'll find it in a second. So let me just tell you about free radicals. Free radicals are going to be particles that have an unusual number of electrons, like a molecule that might have an unusual number of electrons. And in this case, we've said something like that about ions, but please understand, these are not ions. They're not. Free radicals are going to be these molecules that have this weird activity because they've usually given away an electron or picked one up, and now they're going to act like bolts in a china shop. And the china shop are your cells. All those little molecules in your cells are fine china. You need those molecules working the way they do, and all of a sudden this bowl comes in. And what starts breaking? The molecules. So if the free radical, if I'm a free radical and you all are molecules inside of a cell, like this room is a cell, this free radical will break that molecule, bump into that one, break that one, break that one, break that one, and just continue to wreak havoc until it is neutralized. And when we say neutralized, we said that's literally associated with electricity, taking that activity level down, right? So let me tell you what neutralizes free radicals, and those are antioxidants. I do have, does anybody have the PowerPoint that they can actually see where that might be on what slide?
19. 18. It starts, free radicals starts on 16.
16? Really? Really? Okay. Oh, wow. Okay. All right. So I must have skipped it. Like I said, this is why. 16, you said?
Yeah, just the starts on the top. Probably 18.
All right. Well, I don't know where it is, but I'm not making this up. Okay. So y'all just find it in your notes. Here you go. Here you go. Okay. All right. So I just didn't want y'all to think I really was making it up. It is on here somewhere. So here's the thing. Free radicals are natural. They get made. These little particles get made just in nature, just from your own metabolism, right? And so they're going to be made naturally, but we have a way to neutralize them, and the way that we neutralize them are with products that we make called antioxidants. And our cells make these antioxidants. These antioxidants, these enzymes, when you think about these are going to help to neutralize free radicals. So this is all a natural thing. The problem comes in when you're making too many free radicals. And so this is what I need you all to know about. This is why radiation is so bad, overexposure to radiation, because it creates these free radicals that are destructive inside the cell and eventually can even affect the DNA of the cell. So this is, y'all have all heard that you don't want to be overexposed to radiation, haven't you? So this is one of the reasons why. And then other things like chemicals that you might not be thinking about, but food preservatives. You know those little red hot dogs that are really good? Okay, no. You know, bacon doesn't really look that color in nature, right, guys? It has these things added to it. And guess what? Those chemicals that are added to it produce tons of free radicals. Smoking, one of the worst things we can do for ourselves, right? smoking. And that means smoking anything. Yeah. Okay, so smoking. These are the kind of things that we know create unusual numbers of free radicals, and then our cells start to struggle. And over time, we can't produce enough antioxidants to neutralize them. If you've ever wondered about the aging of skin, I'm really wondering about it these days. But if you've ever really thought about that and like age spots and all of those things, these are when all your cells are not keeping up with the free radicals. So, and that's a normal part of aging as well, right? You've heard about antioxidant-rich foods. Now in advertisements, foods will tell you rich in antioxidants, and so you'll pay more for it for that because you just heard that these are good things, right? And so anyway, but they are kind of good things, and we do talk about we are what we eat, and so this is important. But the most important ones are the ones that your own cells make, these antioxidants, these natural enzymes. So free radicals are bad. They're naturally produced, but they're also excessively produced when you are overexposed to bad agents, right? So this is what's happening here. All right, so I think I had skipped that in the. They're the good molecules. Yes, they're the good molecules. Antioxidants are the good molecules. They're good because they neutralize what? Free radicals, which are bad. They're going to be like what? What do we call them? Free radicals. What did I use an analogy? A bowl in a china shop. You're the china shop. Here's the thing about free radicals. I also sometimes call them the other women. Because the other women, they're not going to really just be happy breaking up one relationship, are they? This is something innate in those women. They've got to just go around and keep doing that, right? Until they get neutralized. And I'm not suggesting people go neutralize what somebody else. But I'm just saying that's exactly what I mean. It's kind of like that same thing. So free radicals are bad, aren't they? And antioxidants are good, right? And we've already talked about all the wonderful properties of water. And I've told you about electrolytes. Now I want to talk to you about acids, bases, and pH. And to do this, what I want to ask you is, what do you know about pH? What do you know about pH?
You have to stay within this range.
So, okay, so like most things in the body, our pH should be balanced. And when you say our pH, let's talk about the fluids of the cells. Let's talk about our blood. Let's talk, which is mostly water, is extracellular. The cellular component of blood, if we were to spin and pack blood down, more than 50% of it is just water. So most of it's extracellular. Of course, those important cells are, doing wonderful things. But, okay, so we've got blood, which is mostly water. We've got the water that's bathing our cells, don't we? That's bathing every one of our cells. We've got the water inside of our cells. 65% of the water in a human is inside the cells, is intracellular. Intracellular. So 35% is extracellular, meaning it's found in blood plasma, it's found bathing the cells, and we'll talk about more types of water. But most of our water are inside of our cells, and this is why our cells aren't flat, are they? Our cells are not flat. They're three-dimensional. They're filled with water. They're like little water balloons, right? Don't write that down. So anyway, but they're filled with water. All right. So there's a certain pH that's associated, a normal pH, and that is going to be a range in blood and most body fluids between 7.35 as the low to 7.45. So what's the set point? What should it be for blood and extracellular body fluids? 7.4. So 7.4 is a set point, and y'all tell me you're vacillating around that. So something's keeping you in that range. When something detects that it's high, it's going to bring it back down lower. And when something detects that it's getting low, it's going to bring it back up into the range and keep you in the range. And Erin's exactly right. What is pH? What is it?
It's a form of homeostasis.
It's no. What is pH? It has to remain in homeostasis. That's not what I'm asking you. I'm asking you, what is it? It's about the acidity. What is acidity? we've progressed past the point that we just give rote definitions for things and not really know what we might be saying. How many of you have measured pH on something before? Maybe you've measured it in soil or pool water or pond water, or I don't know, your garden soil, just because of growing flowers, you know, those hydrangeas that are pink and or blue, depending on the soil pH, right? What is pH? Nobody answered this about acidity, okay? Unless you can tell me what acidity means, all right? Who wants to know? How many of you want to know what it is? You're all supposed to raise your hands. Okay, so here's what pH is. pH is equal to the negative logarithm of the concentration of the hydrogen ion. What? What? What does that mean? Oh my God. Okay, look. So I want you to write that down, and then I want you in any class that gives you something like that, I want you to make somebody break that down for you. And I'm going to break it down for you. You ready? What this is, and this is the definition of pH, it's the negative logarithm of the concentration of the hydrogen ion. And that means that this little atom of hydrogen has given up its electron, and it is now a charged atom. So we know what this is, right? Because we know what ions are, don't we? In chemistry, brackets means the concentration of, or what's just a fancy way of saying, how many of these are there? How much? What's the quantification? How many, right? So pH is really just a fancy way of saying, how many hydrogen ions do I have here, right? Are you good with that? Now, I'm going to break it down further, though, because I want you to know what the negative log means, because you can't really understand pH unless you know what that means. So I want to give you some basic stuff here. Y'all probably have heard that pH is measured on a scale to 14. Have you heard that? And you've probably heard that 7 is called neutral. Have you heard that? Yes. It's a neutral pH. Do you know what it means? Does anybody know what it means? All right. So I'm going to tell you what it means. What it means is that if it's neutral, and y'all already know a little bit from what I'm talking about in chemistry, you told me if an atom is neutral, it has equal numbers of what and what? Protons and electrons. It means it has equal number of positive and negative charges. That's what you told me. That's what you told me neutral meant. Well, in a case of in pH, it means that the number of hydrogens are equal to the number of OH anions. The number of these are going to be equal to the number of these. And the fluid itself is neutral. Whatever you're measuring is neutral. There's not going to be one that's higher than another. Are you with me so far? Okay. I told you blood better be between 735. Blood and most body fluids are between these, and that's one of the normal values I do want you to know. All right, so everybody good so far on this? All right. So here's what I need you to know about this negative, what that means. Here's what I need you to know. Because y'all know that 6 comes before 7, and what's here? 5. And what's here? 4. All right. So what this negative means in the definition for pH is as the numbers go down, what happens to the amount of hydrogen ions? It's going up. What this negative means is that this scale is written inversely proportional. So actually, as numbers go down, hydrogen goes up. And as the numbers go up, hydrogen does what? Goes down. Does that make sense? That's all that negative means, is that the scale is written as a positive, but it's really inversely proportional to the amount of what? Which is what pH is all about. How many what? Hydrogen ions are there. You go so far? If you're not, I need you to go back and listen to this slower, break it down, read it, because you might just not like the way my voice sounds, so you might need to read it yourself, just hear somebody else say it, but try to stay tuned right now, okay? So far, I know what this negative means. I know brackets mean just how many, and we're talking about how many hydrogen ions there are. But wait a minute, what does log mean? What does log mean? We've got this when we figured out what negative means, but what does this mean? Well, let me tell you what this means. It means that for every one fold change, just one number change on the scale, it's 10 times difference in this amount. So if I had a 7, but I needed, let's say I had a 6, but whatever. What's the difference between 6 and 7? 10 times more hydrogen ions, 10 times. Is that a significant number? All right, so that's a logarithmic change. Wait a minute. Suppose I needed 7 and I went down to a 5. What'd you say? It's 100-fold change. Here's my math. You're like a math person, aren't you? Lord have mercy, I shouldn't have her up here talking. Okay, look. So if I went from 7 to a 4,000 times more. So this is what logarithmic means. That means that one number change on a pH scale is significant, by God. Okay? So if a one number change is significant, what do you think about tenths? Are they significant too? Yeah, that's a significant difference. You got a patient in your ICU that's gone down to a 7.0, 7.1 pH. You're going to turn your back on them? No, that's a significant pH change. And I'm going to tell you why pH changes are so important in just a second. But right now, take my word for it that it is significant, and you better be remaining in homeostasis. Let me tell you a little bit other stuff too that probably some of you already know. As the hydrogen ions are increasing, this is referred to as acidity. So below 7 on a pH scale, or for humans below a 7.35, below that, you're becoming what? Acid. You've got acidity going. So acid is going to be a problem. If it's higher than this on the scale, then we refer to this as alkaline, or basic, right? Alkaline or basic. So y'all will, maybe you will hear later, maybe you've already heard of metabolic and respiratory acidosis, or maybe you've heard of alkalosis. So now you'll know the pH is off. And with that pH being off, what do you know is changing? The concentration of hydrogen, but really what's changing is really the electricity, if you will, and those solutions, it's changing. The potentials are changing, aren't they? Now, let me tell you why it's important. What did I tell you is the most important of all chemical bonds? Hydrogen bonds. Are hydrogen bonds really bonds? Or were they attractions between polarly covalent molecules? And the polarly covalent molecules we talked about was water, proteins, and nucleic acids. We said they're held together by these hydrogen attractions. Now all of a sudden you're screwing with the hydrogen atoms that are in this all around in the environment. Do you think they're going to play a role in how your molecules stay in shape? I can promise you they are, and these molecules will start to change shape, especially proteins. Proteins will start to denature. If a protein has lost its shape, what has it lost? Its function. Your cells are essentially protein factories. If all of a sudden the proteins start changing their shape, the cells are going to be in crisis. They're going to know they need to build new proteins. That's going to require energy. That's going to take metabolism up. And that's going to usually cause a person to start getting hotter, if you will, which is then going to interfere with what? more protein structures. Do you get what I'm saying? So this is not a good thing. Also, I want you all to tell me if hydrogen is an atom that has the atomic number of 1, what did I just tell you it is? What did I just tell you it has? Huh? It has 1 what? It has 1 proton. 1 little proton. I want y'all to think of just 1 little proton. Okay. It has the atomic mass of 1. That means there's 1 little proton. Is that right? All right. 1 little proton. And it's an ion, so what does it mean it gave away? So now it's just this positively charged, it's this little positively charged thing on here. This is a cell, not a very greatly drawn cell, but this is a cell with a nucleus. This is one of your cells, okay? All right. And in your cells are filled with water, you said. But as a barrier to the outside, you have a cell membrane. But and that cell membrane, it's amazing, your plasma membranes on your cells, how really tough they are. But I'm going to tell you, it doesn't matter how tough they are. You got this 1 little proton, and can it move into the cell? Rather readily, especially if there starts to be a lot of them out here. And if there starts to be a lot of them out here, you're in what? Acidosis, right? Your pH is dropping, you're becoming acidic. And that means you've got a lot of these little guys out here, a lot of them. And guess what they're going to start doing? They're going to start moving into the cells, your cells. They've got a what charge? And all of a sudden, they're moving into the cells. Well, your cells have something in here, too, that also has a positive charge. Does anybody know what K? Potassium. So these are moving in, and they're moving in fast because you're in acidosis or you're acidic, and you think the potassium is going to say, come on in, hydrogen, welcome. Or what do you think is going to happen to the potassium? It's going to move out because like charges do what to each other? Repel. And now you've got hyperkalemia. And my EMTs, paramedics, will tell you that that's one of the most dangerous electrolyte imbalances. Because now you're going to start with arrhythmias. And guess what the heart can do once it's in arrhythmias? It can get a signal to just stop, as Nicole said. This is just another reason that we need to keep things in what, Aaron? That we do need to keep everything in what? Homeostasis, everything, including potassium, including hydrogen ions. Now this looks like a nightmare, these notes. But do y'all understand that pH is equal to the negative, because the scale is written in verse, logarithmic, which means a little change is a big change, concentration of hydrogen ions. Are you good? Okay. Everybody's good? You're going to be able to discuss that for me? Are you? Okay. Okay. All right. That's fair. Now, I need y'all to know about buffers. Buffers. A buffer, because y'all have all heard of buffers, haven't you? A buffer is going to be anything, and we have a lot of buffers in our bodies, a lot of different buffering systems, but it's going to be any kind of system that is going to help you to maintain pH balance. So a buffer is something, another way of saying that is, a buffer is something that helps you to resist pH changes. So y'all, I know it makes y'all crazy. I've had students say to me, you never say the same thing twice, exactly the same. Well, okay. It's a lot of ways you can say things, right? So I just want you to be able to do the same thing. I want you to be able to, several ways you can explain something correctly, right? So a buffer is just something that helps you to resist pH changes, all right? And we have a ton of buffering systems in our body. Why do you think? Why do we have so many different buffering systems in our body? You have backups, but because pH balance is that crucial. It's because pH balance is that crucial. You have a ton of different ways to balance it. Let me ask y'all something. if now that I'm talking about this, you're going to feel a little breathless. But could I have had somebody walking around the room measuring your respiration rates without that you didn't know, that you weren't paying attention to? And what is a respiration? It's one inhalation, one exhale. That's one ventilation. So you do a normal resting adult's going to have between like 12 and 20 inspirations, expirations a minute, right? That's your ventilation. And that's normal at rest. So if we had measured it 10 minutes ago, we could have gotten a number for everybody, and then we measured it again and it changed. Now that I'm talking to you about it, don't you feel breathless? You know, isn't it crazy? Like when somebody, somebody's, you'll have practitioners say, okay, breathe in. You think, wait a minute, I forgot how to do that. Right? Is that right? Keep in mind that patients feel that way too when you all are putting that cold stethoscope on them. But absolutely, that's normal, 12 to 20 a minute. So y'all might want to write that down just so you have an idea of that in case you didn't know that. And they change. They go up and down, but they should stay within your normal parameters. Why are you breathing at the rate you're breathing, and why are you breathing? Why are you breathing? What is the main stimulus that made it so that I could have measured Julie's? It would have been 14 5 minutes ago, and now it's up to 18. She didn't even know I was measuring. Then it's going to come back down to 13. Then it's going to change a little bit. Why are you breathing at the rate you're breathing? What is the main stimulus for breathing? As long as your nose and mouth aren't covered. As long as your nose and mouth aren't covered, and as long as you're healthy, what is the main stimulus for you breathing at the rate you're breathing? And it changes. And why does it change? You are breathing at the rate you're breathing, as long as you're healthy, and there's nobody covering your nose and mouth, and you're not drowning, and you don't have respiratory disease. You are breathing at the rate you're breathing to balance the pH of your spinal fluid. It is a buffering system. Your respiratory system's one of its major functions is a buffering system. So when you lose this major organ system because of respiratory disease or compromise, what is one of the first things compromised? pH. And is the body going to suffer? Yes. Yes. Are all cells going to suffer? Yes. Yes. People usually answer, but y'all, I don't know. Y'all didn't answer. When I say, what's the reason you breathe? And most people say, for oxygen. And, that's if in a healthy person, that's actually the body's least mechanism, because oxygen's being delivered just from breathing. But obviously, if somebody has obstructive disease, COPD, or if somebody has whatever, then oxygen can become the main reason you're breathing, because you do need oxygen. You have about 4 minutes without oxygen. 6, you're done, or lots are going to be done. Lots of things are going to be done after 6 minutes, essentially. So, all right, so you do need oxygen. But anyway, buffers. We have these buffers. Just to look at some of these things on this pH scale and where they kind of fall on the pH scale, you can see now there's one body fluid that doesn't fall into that category of normal pH, and that was urine. Urine can have a pH all the way from 4 or 5, which is really what? Acidic, all the way up to 8 and 9, which is really basic or alkaline. And that can be normal for urine. That can be normal. Any of that range can be normal. We would rather our urine be acidic. And we'll talk more about that when we get to the excretory system, urinary system and whatnot, but okay. All right, how are y'all doing? Energy. We need energy to do work, don't we? And when we think about what that work is, it's mostly chemical reactions that are needing to take place. So I want you all to have a definition for metabolism. And did I already give it to you? What's metabolism? What's metabolism? It's what? Did I give it to you? So it's the sum or the total of all the chemical reactions that are occurring in the body. And by the way, guys, Here are the classes of them. You're decomposing molecules. You are making, synthesis means to make, you're making molecules, and you're taking molecules and rearranging the atoms to make whole new molecules. It's a pretty good thing that's going on inside your cells. And all of these things happening at any given time truly is what we call metabolism. That takes energy, that takes work, and work. To do work, it requires energy. So your body has to have a way to get that energy. We're going to talk about that in just a bit. But anyway, I want to look at some of these reactions. Decomposing means you're breaking something down, doesn't it? That's what that means. So when you eat that lasagna, but when you eat that lasagna or you eat that food, you know, you're eating these big molecules. You can see them on your food labels, can't you? Carbohydrates, proteins. You see those? I see mostly carbohydrates when I look at my labels. But anyway, carbohydrates. These are huge, big molecules, but you can't absorb those. So when you get those into your system, you have to decompose them to smaller units. And I want you all to write down two words. The first is monomer, and the second is polymer. Mono means what? One. Poly means what as a prefix? Multiple, right? So monomers, these subunits called monomers, make polymers, right? Are y'all good with that? Do you see that? And when we take in polymers, must we break them down to? Monomers. Everybody good with that? So we break them down, and we can do that. We can decompose them. How about synthesis? We can take these monomers and we can put them together, making these big polymers, and make them into what we want to make them. So we can take these building materials, these monomers, and make polymers. Go ahead and write down now, because we will get to it in a minute, but I want y'all to write down that amino acids are the monomers that make the polymer that we call proteins. Okay, go ahead and write that down. And we're doing that. Our cells are doing that at a phenomenal pace. Hey guys, those enzymes that I told you that act like antioxidants, what was an antioxidant? A good thing that helps to neutralize free radicals. Those enzymes, those are proteins. Don't you want to be able to make those? Don't you wish you could make as many as you used to? Okay. But yes, we want to make those. We want to make those enzymes. Our cells need to make those, and those are just some of the proteins we're making. We're making so many different types. It's actually hard to get your head around. But anyway, we're definitely doing that. And then these are called synthesis reactions. And then sometimes we're taking molecules and we are breaking them down and rearranging their atoms and coming up with totally new things that we need in the cell. So these are called exchange reactions. All of them combined add up to the sum. And what do we call that? What do we call that? We call that metabolism. We do. All right. So look, reaction rates. I think I maybe told you that our cells are doing things at phenomenal paces, right? Maybe I didn't do this because I don't know, I'm getting confused with what class I told what. But anyway, for all of this to happen, it means that we have to have the building materials. We have to have those building materials in some way. We have to have them as polymers, or we have to have them as monomers, because we can't make something that we don't have the building materials for, can we? That would be magic. All right, and that's not happening. So we have to have them, and we have to have them in the right amounts, because these reaction rates are based on a lot of things. Some of them are that they're present, but they're present in the right amount of concentration. Also, that our temperature is a certain degree, because the temperature is going to cause these collisions to happen at a certain pace, right? If the temperature slows down, do as many collisions happen? No. So we have to have everything kind of being just right. I want you all to know that the term catalyst is, for me, for my purposes, you're not right. No, okay, but whatever. But for all intents and purposes, catalysts, these are enzymes that are proteins. So I want you to know that. I want you to know that catalysts are enzymes that are protein. They're protein in nature, and they make things happen quickly, incredibly quickly. be really almost beyond our comprehension quickly. So catalysts are things that are going to speed up reactions so that our cells can do things at just the right amount of time that you need them done. Without the catalyst, the cells are slowing down tremendously. And catalysts are what? They're proteins. And protein structures dictate how they function. And one of the things that I know that contributes to their structure is what kind of weak bond? Hydrogen. And here's something I know that interferes with hydrogen bonds. I know two things now that interfere with hydrogen bonds. What are they? Temperature and pH concentration. Thank you. And so all of it, isn't it just great when it comes together? Yeah, that's what I think. Science is awesome. Yeah, and that's exactly right. So we know they speed reactions. We've got to have them. We've got to have them just as we need them. All right, so I'm not going to ask you about this. If I go buy something, does it mean you're going to need it for my test? No. Doesn't mean that you shouldn't read over it because you have inquiring minds and you want to know, but I'm not going to test you. All right, now I'm going to introduce this to you. We'll take a quick break and come back. Guys, so we have these atoms of elements. Y'all told me the four predominant ones were what? Thank you. Do you think you're going to need to know that for the test? I can guarantee that on the test, okay? So you're going to need to know. And you said that these things make up 98+% of who you are, right? How they're playing together, making these huge macromolecules. These are the four classes of macromolecules: carbohydrates, lipids, proteins, and you can just write nucleic acids if you will, and I'll talk more about that. Nucleic acids are made of nucleotides. But write these four categories down. These mean these are huge molecules made of a lot of those four things plus other atoms, right? But a lot of these are made of what? Carbs, oxygen, nitrogen, and hydrogen, right? So we know that, plus other molecules, really important atoms as well. But these are our major categories. So we're going to take them one at a time and figure out some basics of them. Most of the basics meaning their functions. Okay, let's take a quick little break. Let's take 10 minutes, okay? 10 minutes. 10 minutes. Get up and stretch your legs or something. Okay, so we're back. We're back. And we're going to talk about these four major organic categories: carbohydrates, lipids, proteins, nucleic acids. So let's go ahead and start. And a main thing I do want you to know about organic chemistry and organic categories, I think I've already told you this, is that what is the element that is the backbone for these? Carbon, right? So I had told you that carbon is that backbone, and I've given you a definition for monomers and polymers. So we're pretty happy with that, understanding that definition. Now let's look at carbohydrates. You all call carbohydrates, or most people call them sugars, right? All right, but what I want you to know are some basics. Now, sure, I keep these PowerPoints not to read to you, but just to make sure I try to remember what to tell you. But anyway, I do want you to know that if you see a molecule that ends with the suffix "-ose" or the root word "saccha," you're dealing with a carbohydrate. That's what you're talking about. It's a carbohydrate. And these are, as far as this category goes, these are this is one of those four categories that become the building materials for your cells. And I can't emphasize that enough. Like, these are the molecules that will literally be physical building materials for your cells. So that's one of their functions. That's one of the functions of carbohydrates. But another major function I want you to know about is that this category, this is where we get our cleanest, quickest source of fuel for our cells. That means energy for our cells. We get them from this category. So when somebody goes on a completely carb-free diet, then there's really no such recommended thing, because you should always be getting a minimum number of carbohydrates. But when somebody does, will they lose weight quickly? Absolutely they will, because if their cells don't have carbohydrates, they're going to have to be burning something else for energy. and the something else is going to be fats, and we're going to talk about fats in a minute. But if you take out carbs from your diet, even in a fasting period of time, 12-hour period of time, you're going to start burning fats for energy, because can your cells go without energy? Because you said your cells are always doing what? Work. 24/7, no resting, no smoke breaks, right? Working. So they've got to have it. But listen to what I'm saying. For your cells, for our cells, the cleanest, quickest source of fuel is from this category. It's carbohydrates. And now listen to this. How many different tissue types do you have? 4. How many cells make up those tissues? Over how many? Over 200, right? There are 2 types of cells that can only use carbs for energy. You want to write these down? These 2 types of cells that can only use carbs for energy are this: nerve cells and red blood cells. So going on a no-carb diet, does it make any sense for your homeostasis? No, because what system controls all homeostasis? Nervous system. And what system depends exclusively on carbs? Nervous system. This is why people who drastically reduce carbs from their diets will start acting almost a little confused and almost even drunk, right? Their nervous system is depressed. It's going to throw other things off as well. So there's a smart way to handle it. The thing in this country is that all of us, not all of us, some people aren't craving carbs. How many of you have a sweet tooth? Okay, so I definitely do too. And actually, as far as evolution goes, that sweet tooth helped us. It was an adaptive trait that helped us to survive. And so that's why so many people in our generations now really do have that sweet tooth, because it really was an adaptive trait helping our ancestors to survive. But anyway, so some cells have to have this. So what are 2 functions I just gave you? Those are 2 cells that are exclusively need this for energy, was the nervous system and red blood cells. But what 2 functions of carbohydrates did I give you? Building materials, building blocks, building materials for your cells. Just like a contractor can't come to your house and build a sidewalk unless he has what? Concrete, right? And this is like the concrete. I mean, you've got to have it. You've got to have these carbs. So make sure if you know SACA and OS, that means that. Now, not all carbohydrates are good carbohydrates. Some are said to be empty carbohydrates. That means that have you ever heard that they're empty calories? Have you ever heard that? Things that have empty calories, carbohydrates that are empty calories, they can still be used for energy. But what they can't be used for is building your cells. So that's why you've heard that before. And honestly, you should try to get carbohydrates that aren't empty. But you should try to get the ones that are actually going to be able to be used for building materials and used for energy. So those are what? Fresh vegetables, fruits, those kinds of things, right? I'm not going to go too much into structural formulas. I did have you all know glucose is a monomer, isn't it? And I did have you all know that particular formula, and we're going to come back to it in just a little while. I'm promising you that. But when you talk about disaccharides, a monosaccharide just has one of these circles, right? Circles of, and everywhere there's a point right here on the circle is actually a carbon atom, but you don't need to know that. But anyway, and some of them have 2 monomers, they're di. And so, you know, some of them are polysaccharides. That means they have how many of these rings? Multiple, right? Oligosaccharides are huge, right? So these are going to be at least 10. So, you know, whatever. I don't care that you know that part too much. Now, I have already told you all about glycogen, haven't I? And I told you that glycogen is an energy storage molecule of glucose. And I said that when your carb levels start to get high, your glucose levels start to get high, what endocrine gland will produce insulin? The pancreas produces insulin, and insulin escorts some of the glucose into your cells to be used right then. but it will also initiate glycogen formation. And where did I tell you that will be stored? In the liver and muscles, right? So that between meals, you have that you can go to break down glucose so that you can keep your blood glucose levels where they need to be. We don't need to graze 24/7, do we? So, right, we don't because of this. All right, now, these are just some examples of carbs, and that's fine. Sometimes carbs will end up playing a big old carbohydrate. And let me show you a formula for this, maybe. Not glycogen. Okay, never mind. It doesn't give you one. But sometimes carbohydrates will play with the protein, a glycoprotein. And sometimes they will play with fats, lipids, glycolipids, right? So sometimes these molecules end up playing with each other, forming really huge molecules. But they're going to be molecules that are actually needed in the cell for specific functions. Now let's go to lipids. If I don't say it, are you responsible for it? Okay, so just so you all know what to study. I have some students who really don't trust me. And I don't know. I don't know how to tell them to trust me. You know, but trust me. Study what I'm telling you. I'm telling you what you need to know, okay? All right, so lipids. Lipids, what do we call them? Yeah, we call them fats, don't we? We call these things fats. So these are good things or bad things? Okay, just like with most things, it's good and bad. But actually, they're absolutely necessary. I do want you now, why am I telling you all specific things I want you to know now? Because later we're going to do what? Build on it, right? So I want you to know now that if you hear these terms, you know you're talking about a lipid category. So fatty acids, that's kind of in its name, fatty acids, triglycerides, phospholipids, well, this is, lipids is in the name. Eicosanoids, this is an entire group of hormones. Do we love our hormones? Yes, we do, don't we? And steroids, also another entire group of hormone-based or hormones that are lipid-based. So these are going to be things that are absolutely necessary for our cells to function. We do have to have a certain amount of lipids brought into our system as building materials for our cells. I want you right now to, let's look at this phospholipids, and I'm going to try to find a picture. There we go. Guys, these phospholipids, this is one phospholipid, and what I want you to see on this, and this is, you know, certainly you would never have to draw it, but I want you to think about it as like having a little head up here with two little tails, okay? And so that's what you're seeing here, a head with two little tails, almost like a clothespin type of thing. This little head is going to love water. It's going to be hydrophilic, but these little tails are hydrophobic, which means that water repels them. Are you good with this? So this is a phospholipid, and this phospholipid, what I want you to see, because of its, and again, structure dictates function. Are you kidding me? I don't have a picture of this. Really? Okay. Well, that's crazy. I'll have a picture of it in the next chapter. But I want you to think of these phospholipids. They make up more than 70%, as up to 90% of our plasma membranes. And let me tell you what they do. It's called a bilayer of phospholipids, a bilayer. I gotta find a picture. Wait a minute, because I just can't stand up here and make motions that it's gonna look right. All right, wait a minute. I am going to find a picture of this. Even if I have to open a whole nother thing, which I will do. Really? I won't do it if I can't find it. Hey guys, can y'all see up here? Can you see this? All right, this is what, and this is just for now, just so you have a visual
with this. This is even better. Do you see the little heads here and the little heads here? So you've got the head with the little tails down and the head with the tails up. So they're pointing at each other like this. Do y'all see that? The tails are toward each other like this. This bilayer, this is if you took a cell and you just did a little slice through the plasma membrane, you can see these phospholipid heads here, and tails pointing toward each other. That bilayer is a fat layer that is our plasma membrane. So when you think about this, you can think about it almost as delicate as if you had a, where am I? Oh, I've already skipped. Is if you had, what would it look like if you dropped a drop of oil into water? What would that look like? What would it look like? Yeah, it would. You could see that little oil drop in water. Why? Because the oil doesn't like what? The water, and it won't mix. It's hydrophobic, isn't it? Those little tails are hydrophobic, and when the phospholipids line up like that, they're keeping the outside water out and the inside water in of a cell. And that bilayer seems incredibly weak, doesn't it? When you think about how that seems like, okay, are you telling me that our cells just have this like little thin lipid external barrier keeping the outside out, the inside in? Yes. And it's strong enough. It's strong enough that these phospholipids, that's one of their main functions. And I am going to want you to know that that is a main function of phospholipids, is that it acts as the plasma membranes of our cells. A bilayer of it acts as the plasma membranes of our cells. Okay, so that's a main function there. And we already know that this is a category that we're going to end up finding a lot of hormones fall into this category. And when we think about fats, yes, every one of our trillions of cells are the barriers, the plasma membranes are fats. But embedded in those membranes is cholesterol molecules that act as the studs of your cells. Cholesterol is a fat, and it gets a bad name, doesn't it? Because people think about cholesterol. Oh, we don't want cholesterol. Well, yes, every one of your cells need cholesterol. It's the studs inside of your cells' plasma membranes. It would be like if you went to your house and all of a sudden somebody took the studs out of the walls in your house. And what would happen to your house? It would fall down, wouldn't it? The thing about cholesterol, though, that molecule, is that we can make most of what we need, as much as 85% of what we need. So do we need to be taking it in our diet? Not very much. Usually if we're healthy, we can get rid of the excess that we take in, but we really don't need that much in our diet because our cells, through synthesis reactions, can build the cholesterol you need for the cell structures. So that's just one example of another lipid that we're really happy about. When you think about fats, should an individual, an organism, have a certain amount of fat, percentage fat? Yes. Yes. You have to have a certain percentage fat. For one thing, you have to, because some of our organs, their stability, like our kidneys, are based on that. And it's not just stabilizing them, it's also insulating them. And under our skin and our hypodermis, we should have a certain percent fat. So fat acts as a structural component for our cells. It acts as an insulator, as a stabilizer for our organs. There are whole classes of hormones that are lipid-based, right? So here's the last thing I want you to know as a function. It is a wonderful alternate energy source. Why do I say alternate energy source? Where should we be getting our energy for our cells? What's the cleanest, quickest source of fuel? When I say fats are a great alternate energy source, let me tell you why we call them alternate. But they're wonderful, and we should have enough fats for that time. Because, guys, we haven't always had Burger Kings on the corner. And we haven't always had, bags of M&Ms. And we haven't always had that, right? So we really do need fats for times of fasting and fats for times of famine. We need those fats, and they can be used for energy in the cell. But when a fat gets broken down for energy, what I'm talking about not being as clean a source of fuel is that there will be a byproduct that gets made that it's going to have to be dealt with. When fats get used in a cell for energy, you get a byproduct of the breaking down of the molecule called ketone bodies. And have you ever heard of ketone bodies? Who's heard of ketones? Okay, some of you have. So good. I need every one of you to know that when you burn fats, they're great for energy. That's a great thing. So you're supposed to be able to. But your cells are then going to have to deal with what are called ketone bodies, which can put you into something called ketoacidosis. When I just said ketoacidosis, what did I tell you had changed? pH. The pH. What did I tell you you don't really want to change in your body? pH. So then your buffers are going to have to work overtime to try to correct the pH. And typically they can. When you all have heard of there is a safe way to lose weight, have you ever heard of that? What they're talking about is there's a safe amount of ketones you can put in you can deal with at any given time, right? Any questions from me? So fats have a lot of functions. One of the functions is to serve as an energy resource, and that's good because we need them for that. It's one of the reasons that women are so much better at saving calories than men. And any extra calories in women can be converted to fat. Why is that a good thing?
That's a good question.
What'd you say?
That's a good question.
Yeah. Why is that a good thing that men can have normally between 10 to 20% body fat, but women's normal body fat can be right at 20 to 30%. It can be normal for them. So women have a higher normal percent body fat. Why? But why do we have the hormones that we got? Because women have a 9-month gestation that they may face during a time of famine. Now, you know, we don't have as many periods of famine as our ancestors did. But our ancestors went through periods of time of famine. And did they need the extra body weight? You'll hear about body weights now needing to be, for women of gestational age, you'll hear that they need to be a certain percent. But I think we've kind of overstated that because there are some, you also see in areas of this world today where famine is a real thing. Hunger is a real thing. And you'll still see women that are going through gestations, and you wonder how do they have the body fat to get through this gestation, right? That they need. And then obviously, is it a higher risk pregnancy? And obviously, are those neonates being born at a deficit? And then obviously, are those neonates having higher mortality rates? Yes, they are. But women's hormones are designed to store body fat and water in time. And so we're animals. Let's not forget that, you know. No, so we are though. And so this makes hopefully sense to you why women and men are different, aren't they? We should celebrate those differences, I feel like. Anyway, so adipose, I would want you to know when you talk about adipose, this is a tissue that is composed of cells called adipocytes. Adipocytes are fat cells. Adipose is fat tissue. Fat tissue is made of fat. What are tissues made of? Cells, right? So you guys, when y'all study, do you talk out loud? Do y'all know that talking out loud is, while you study, is one of the best ways to retain information? The person talking is the person usually typically learning, which means that this whole lecture-based thing is crazy, because y'all should be talking, right? But it is often why when you get to graduate levels, because I have some people in here who've already had degrees and stuff, when you get to graduate levels and you're really in your field, you end up doing most of the talking and the teaching in those classes.
because you've gotten the foundation you need, and you're becoming more expert about it, and it really can help you. But you can do it now too. By the way, our nursing program and most nursing programs throughout the state, I'm getting off on a little tangent, but this is important for you to know. Only a few of you are not going into nursing, the rest of you are. Our nursing program is based on a collaborative type of learning system. They do not teach you. When I say they don't teach you, I'm not saying they're being mean. They let you teach yourselves because supposedly that's the best way to learn. I agree with that. After you've had the foundation, you can do that. But anyway, so just get ready because you need to start doing that now. You need to start teaching yourself. You need to start talking out loud. You need to start looking at information with a whole new set of eyes, thinking, how would I explain this to each other, to someone else? How would I explain this to my peers? Because when you get in those nursing programs, that's what you will be doing. You will be teaching each other and getting up and doing that. So start now. You can't start soon enough, okay? Yes.
I have a question when it comes to ketoacidosis versus your keto diet. Like, what's the difference? I mean,
It's no difference. They're getting you into ketoacidosis. Those keto diets are really getting you into that burning fats.
Okay.
And there should be a safe regulation on how to do it. Please don't think that I'm telling you that this is unsafe, but there is a rate that it's safe. And then when you think that, and every individual is kind of different with that, but here's what's also unsafe. You'll hear about people who get put on really low carbohydrate diets and fat and proteins or what they're burning. You should really never burn proteins for energy, never. If you're burning proteins for energy, you're wasting away. Okay, so, but fats are a good source of energy. They're good source of energy. But for people who are doing them at a fast pace, they're usually, hopefully, under doctor supervised care. And what they're thinking is that the extra weight is actually as dangerous as them being in ketoacidosis. Do you get what I'm saying? So like gastric bypass surgeries, and you're talking about people who are like 100 plus pounds overweight, they do get put into a really serious ketoacidosis situation. But the extra weight is putting on so much. You know what I mean? It's just
good outdated fat.
Yeah.
Gotcha.
Thank you. Easier way to say it. Yeah. Thank you. Yeah. All right. So lipids, and so we know lipids aren't a bad thing, aren't they? We're going to talk more about lipids when we get to the nutrition part, and this whole good and bad cholesterol thing, because you'll hear about total cholesterol. So total cholesterol values mean very little. They mean very little to nothing. You have to see what types of cholesterol, and there are different types of cholesterol that contribute to the total. So you guys have heard of good cholesterol. One of my students just not long ago said they remember HDL is the good cholesterol because it's happy age. HDL is the good cholesterol. So you can actually have a whole lot of this, and that's fine. And the LDL is what we kind of consider the bad. When somebody gets a total cholesterol number, it means nothing until they look at this ratio. And the ratio indicates whether they're at cardiac risk. Okay. I've seen people with really low total cholesterols at like 140 milligrams per deciliter at high cardiac risk. Why? Because they had almost none of this detectable. It was all this. Without this stays in the blood vessels. If this is staying in the blood vessels, what are the blood vessels doing? Clogging and hardening, right? But as long as you have a whole bunch of this is transporting this out of the bloodstream into the cells. Whatever. That's too much detail. But anyway, I just want you to know cholesterol does kind of get a bad name, and we do need it, but we don't need to take in as much as we do. Now, there is something called, and I want to talk to you about this, there's something called hypercholesterolemia. That's a big name, isn't it? Hypercholesterolemia. Hyper means what? High or a lot. Cholesterol means, and emia as a suffix always means in the bloodstream. So hyper always means high or a lot of. So a lot of cholesterol in the bloodstream.
there is something in one of your deeper insights, either this chapter or the next, that is talking about familial hypercholesterolemia. That's a big old mouth word, isn't it? But mouthful. But anyway, so what does that mean? That means that you've inherited high cholesterol, right? And let me say this to you guys. The people who inherit this, they're dying of heart attacks in their 20s and 30s. They have outrageous cholesterol numbers and triglyceride numbers. Their numbers are just outrageously high. And they are dying very young of this. Now, what's the problem in these people? And you'll read this in a deeper insight. But our cells, for anything to be allowed into our cells, if we're a cell, if this room is this, I keep doing this because I pretend like this room is a cell, one human cell. The ceilings, the walls, the floor are plasma membranes, which we said is just really a little lipid thing, right? But it's keeping the inside in and the outside out. Is that right? Inside in, outside out. So let me tell you, for everything that has to come into the cell, there has to be a protein receptor that recognizes it. So with people who have familial hypercholesterolemia, they don't make those receptors. So there's no doorway for the cholesterol to come in. So where does it stay? It stays outside in the bloodstream. And their arteries, by the time they're late 20s, 30s, whatever, look like 80, 90-year-olds. So too few receptor proteins that allow that in and work. So we've got to have all that working, right? And you'll get to that in one of those insights soon. But okay, proteins. Everybody ready to hear about proteins? Are you ready? Yeah, and I can't say this enough. The Greek word meaning of first importance. That might be something y'all want to pay attention to. Because our cells are essentially, our cells can make carbohydrates. Our cells can make lipids as the building material for the cells and to use as energy. But our cells are essentially what kind of factories? Protein factories of first importance, okay? These are the most versatile molecules in the cells and extracellularly and just whatever. They're running the show. I've already given you all one example, one whole class of examples of proteins that I told you speed up reactions. What were they? Enzymes. What was that word that speeds up reaction? They're called catalysts, right? They're called catalysts. That's just one type. Now here's what I need y'all to know. I need y'all to know these monomers that build your proteins. These monomers are called amino acids, and you have 20 different ones, 20 different types of amino acids. How many of you all have heard in nutrition class, or you've heard somewhere, maybe even just on TV or something, or on your food packaging, that something is an essential nutrient, or it's an essential amino acid, or it's an essential whatever? You've heard that, right? Have you not heard that? Has everybody heard that? What does the word essential mean? It means what? In nutrition, it means something different than outside of a nutrition classroom. Because let me tell you, all 20 are essential, the way you talk about it outside of a nutrition classroom. That essential to you before you think about nutrition, essential just means you need it, right? Is that right? Yeah. But when you're talking about nutrition and you see that something contains an essential vitamin, an essential mineral, an essential amino acid, it means that all of those things are needed, but your body can't make this one, so you better include it in your diet. It means that an essential one means your body can't make it, and there are about 8 of these that you can't make. So what does that mean? You need a variety of what in your diet to make sure you could get those 8. A variety of what? Proteins. And when you ingest those proteins, they have to be broken down for their amino acids to be absorbed. And then can you use those amino acids to make your own proteins? Yes. And do you need all 20 different kinds of amino acids? Yes. You need all 20 different kinds of amino acids to make your very varied proteins that are going to have very varied functions. Name some proteins for me other than catalysts. What else are proteins in your body? What else are proteins in your body? Keratin, soft and hard keratin, that's a protein, isn't it? If you say you have an antibody against something so you can't get that disease, those antibodies are, guess what? Proteins. Your muscles, if you had, who likes steak to eat? Who likes steak to eat? Okay. What is steak? Muscle, right? It's the muscle part of whatever you're eating, whatever animal you're eating. It's the muscle of that. And what is steak? What do you know you're getting a lot of when you eat muscles? You're getting protein. Well, that's because our muscles too, and other animals' muscles, are almost predominantly protein. Inside those muscle tissues are made of cells. Those cells are predominantly contractile proteins. So that y'all have probably heard of actin and myosin, haven't you? Whatever, you will soon when we get to the muscle section. But yeah, those are proteins. We have so many different, thousands of different types of proteins that our cells make, and our cells need them all functioning so that they can work the way that they're supposed to. Now, these amino acids, when you think about these 20 different amino acids, they don't all end in INE, but many of them do. Not all of them, but many of them end in INE. So when you hear this, when you hear like arginine, cysteine, tyrosine, methionine, yeah, so these are amino acids, fine. Now, the thing about them, and what I would want you to see, is that they have this basic group that stays the same. And then they have a reactive group that's going to be different. And this dictates how they act. So does tyrosine act like arginine?
No.
No, because the structure is different, isn't it? And the structure dictates. And let me just tell you something. Where if you were supposed to have tyrosine and instead it gets replaced with arginine, is that protein going to work the same? No. You got to be kidding. Are you serious? It's close. Not going to work the same. So keep that in mind. So 20 different amino acids. They all must be present for you to make the proteins that you need. And here's what I want you to know about protein structure. And I definitely want you to know about protein structure. Now here, let me say this. Can proteins be broken down for energy? But you don't want them to. Because if proteins are being broken down for energy, it means that everything is suffering at this point. Y'all have heard that cancer is a wasting disease. Have you heard of that? Because what ends up happening is the body is really cannibalizing itself. Carbs aren't being used right, so they burn all the fats away. Fats are gone, and now muscle's wasting because for energy, and all homeostasis is thrown off at that point. So they can be used for energy, but you would never want them to be, right? All right, so I want you all to think about the structure for a second. So we said proteins are going to act as catalysts. Proteins are going to be the building materials for our cells. They're going to also act as building material for cells. They're going to end up making up most of certain tissue components. So proteins have a lot of varied functions. They're going to help the cells to carry out movement from things on the outside of the cell to the inside of the cell. Because we said the barrier is a lipid-based bilayer phospholipids. But what acts as doorways and windows? Proteins. They're the ones that are acting as doorways and windows, so we better have the ones we need, right? So exactly. Now I want you to think, to understand this, because this is important to understand, really, to figure out how proteins work. You've got to know how they're made. You really do. So, because this is basic biochemistry here, and you can't really understand life without understanding protein structure. I want you all to think about 20 little boxes of beads. And the beads look slightly different, right? So these beads might be like shells, and those beads are marbles, and those, but we have 20 different boxes of beads, right? And we got to make a protein. We've got to make a protein molecule. And this is what your cells do. So what your cell's going to have to do, and it's hard for y'all to see probably in the back, but can y'all see this looks like a chain of beads? Can you see that? So the first one has to come up to a workbench, and you have that first one, and then at this workbench inside your cells, you're going to hook a second one to it. Then you're going to hook a third one, and then a fourth one, and then a fifth one, and oh my God, it's getting old now. But okay, so you're hooking them together in a chain. This is called the primary structure, which means first. The first structure of a protein is that you know exactly in the 15th position which amino acid that is. It means that you know exactly in the 102nd position what amino acid is right there. You know what is there. These amino acids get in these positions in a very particular way. Are you with me? They come up to the workbench in a very prescribed way. And that sequence of amino acids, knowing them, is the primary structure of a protein. Now I want you all to picture that I'm holding this chain of beads because I'm finished making that primary structure. Do y'all see it? You see it? Kristen, you see my chain of beads here? You see it? Right. After that chain is formed, because remember, these are amino acids, aren't they? And I could go back to the structural formula of amino acids. And what I would show you if I went back to those is that these are actually polarly covalent molecules. What's going to happen here in this little chain, as soon as it's made, this chain is either going to form a ringlet and stay like a ringlet. Y'all have all seen ringlets, haven't you? A little curly tail. Or it's going to fold like an accordion, like you just folded up a paper accordion, you know, like a paper accordion. What dictates how that secondary structure happens, whether it's a ringlet or whether it's a folded accordion, are going to be the hydrogen bonds that are holding it like that. Are hydrogen bonds weak or strong? They're weak, but are they strong enough to hold that structure? Yes. Yes. And so the second structure is how the primary structure is going to act once it's made. Does that make sense? Now let me tell you about the third structure. The third structure is that once that is either formed a ringlet or fold, the whole thing collapses on itself. So for example, oh my God, I can do this faster. Not really. All right, so let's say that this is my chain. Oh, really? Prettier than this one. I can't go too fast. But let's say this is the sequence is the primary, but how it did that is the what? And then all of a sudden, that whole chain will fold on itself. That's the tertiary structure, which is the third. It might fold on itself. It might fold like this. You get what I'm saying? It'll fold on itself. And then that whole chain might play with another chain and another one and another one. That's the fourth structure. Who has questions about this? What's the primary structure? Knowing which amino acid is in which spot. That's the primary structure. What's the secondary structure? Whether it does what? Folds or ringlets. What's the third structure? Whether the whole thing folds on itself or how it folds on itself. And what's the fourth thing to take into consideration? How many of these are playing together. Is that right? And guess what, guys? Guess what? And y'all need to be paying attention to this because this to me, it blows my mind. This blows my mind. It really does. This is one molecule, one. And we understand that every one of these four chains had to be initially started with what? One amino acid that came up and got a line at a time. And then that chain did that, and then it folded, and then it got with other chains, and this is one molecule of hemoglobin. Hemoglobin is a protein, and y'all have all heard of hemoglobin, haven't you? Hemoglobin is a protein that is going to function, and I want y'all to know this is an example of a protein. It's going to function by delivering oxygen to our cells. Hemoglobin is the main protein inside of your red blood cells. Each of your little red blood cells, each one of them, are filled with about a third of their content is this. This is one molecule of hemoglobin, and each one red blood cell has 280 million of them, of these. Can we get our head around 280 million? No. One red blood cell has 280 million molecules of these. One red blood cell, its function is to deliver oxygen to your cells. Deliver those oxygen to your toenails, fingernails, hair follicles, liver cells, kidney cells, all your cells that are mostly stationary. But blood is circulating around, and red blood cells have what? Hemoglobin. That is like a little train that's holding on to oxygen. It's going to be just delivering oxygen to your tissues. So your tissues don't what? Die. Because will your tissues die without oxygen? Yes. Cover up your nose and mouth. How long do you get? Not long. Right? Do you need this? Yes. And one molecule of this has 4 chains of these amino acids that have come up and gotten in line in a very specific way. Why in the heck is that important to know? Because one amino acid out of order is the disease we call sickle cell disease. Have y'all ever known a sickle cell person? Do you know somebody with sickle cell? How many of you know somebody with sickle cell? Raise your hands high if you know somebody with sickle cell. I know you know them. Okay, so raise your hands up high. All right, sickle cell disease is the most common inherited disorder of darker toned people. I don't like saying black people. I know some white people with sickle cell. I do. I worked at UVA. I saw some people that were very light skinned. I also don't like black-white because it doesn't make any sense. But it is the most common inherited disorder of darker toned people. And it's absolutely explained why it is. You can explain why it is. But let me tell you about this disease, sickle cell. A lot of you all raised your hands, and so you probably know as much about it as maybe I do. But this is a devastating disease. People who have this one amino acid that just got out of order and inherited the recipe that did that, they have a disease that's devastating. And people who have sickle cell disease, and this is the truth, people, well, can I call the trait, use an A to represent the trait? People who have that recipe, the recessive recipe for that, and they got it from one parent and another parent, they died before they got to reproductive ages before modern medicine. They died. They did not make it. Sicklers used to not make it. They didn't. And even the ones that make it now, it is devastating. It is, there are 2 patients I've ever seen that I know were in true pain. True pain. And one of them was a sickler. And it was undeniable. The pain in this crisis. I've seen a lot of sicklers in crisis. So I've seen a lot of sicklers in pain. But this one sickler I remember, never forget now, as long as I live. And I did not, nobody thought he was going to make it. And he did make it through that crisis. A couple of days later, I went back to see him. And I asked him, what did his pain, could he describe his pain to me? And he started to cry. This is a young man. Well, he was young at the time. he started to cry. He said, you know, no one's ever asked me to describe that pain. And he said, have you ever stepped, and I'll never forget him telling me this, he said, have you ever stepped on a piece of glass, like on your heel, a piece of glass? And I immediately had that sensation, almost like electricity goes up your spine. Y'all know how that is? He said, that's how it feels with my blood moving through my tissues every day. Constant. And I was like, okay, I get it. I mean, I don't really get it, but on board with you, buddy. Yeah. He was grinding, during that crisis, he was grinding his teeth so hard that it was breaking his molars, they found out. It was so loud, you could hear it like all the way down the hall. It was crazy. It was crazy, his crisis. But anyway, and it's doing irreparable damage every time they go into a crisis. And he wouldn't live to the age he was without modern medicine. But what happens is, what we found out, and darker tone skin tone, no such thing as black and white. There's rainbow skin tone. There's no two people in this class with the same skin tone. We are one race, guys. Homo sapiens, one. But people with darker tone skins have evolved, have come from equatorial regions of our Earth. Is everybody listening to this? These equatorial regions are hotter. And the hotter equatorial regions require darker melanin. Why? Because it protects you from radiation from the sun. So darker skin tones have predominantly come from these equatorial regions because it protects from radiation, which I just told y'all radiation is not a good thing, right? So that's protective. That's an adaptive trait to have darker tone melanin. But in these equatorial hot regions is also where there are mosquitoes. Mosquitoes that carry a disease that still causes more than 1 million deaths in the world today every year. More than 1 million, and it's mostly children, die from malaria every year. Every year. Malaria is a protozoal disease. This protozoa loves red blood cells and requires red blood cells as part of their life cycle. So let me tell you about humans in these equatorial regions. The humans that had normal hemoglobin, normal from their mom recipe, normal from their dad, they died from what? Malaria. But the ones that had a normal recipe for hemoglobin, so they didn't go into crisis, sickle cell crisis, they got to live, but were carriers of sickle trait, had an advantage to survive malaria. So darker tone people that have come from equatorial regions where malaria still today kills an outrageous number of people. If they were heterozygous for the trait, if they were carriers of the sickle trait, they got to live because they didn't have malaria and they didn't have sickle cell. But if they made it with somebody who was the same, they had a 1 in 4 chance of having a child that was a sickler. And a 1 in 4 chance of having a child that wasn't going to be able to survive malaria. But a 50% chance of having a child like themselves that could survive both. Do you get what I'm saying? So it absolutely, in nature, we understand the science of why this trait is so predominant in darker toned people. It's so predominant because it gave an adaptive advantage when it was heterozygous to survive what? Malaria. And now, here's the beauty. Here's the beauty. I think about that young man sometimes. But here's the beauty. Now, sicklers, with modern medicine and preventing crisis like he had, because he did some serious damage to his organs during that crisis, but trying to prevent serious crisis, they can live normal lifespans. So is that like a hallelujah and an amen all rolled into one, guys? That is a hallelujah and an amen rolled into one for modern medicine, isn't it? Let me tell you about sicklers. And I know my EMTs and my nurses see this. They're the most discriminated against patients that you'll see probably in a hospital. It has nothing to do with their skin tone, because I've seen people with the same skin tone be the ones discriminating against them. And let me tell you, it didn't happen more than once in my site. They get discriminated against because they get told, they get labeled as drug seekers. They get labeled as drug seekers because their pain threshold is so much. That has nothing to do with them. That is no slight on them. What do we know about pain medications? To get to the same level the next time, what do you have to have? You have to have more to get to the same threshold of pain. It is not their fault. If you would like to see what a sickle red blood cell looks like going through a blood vessel, then go please back on and look at it under a microscope. I'll show you all when we get to hematology. But people should not be discriminating against them. They should not be withholding meds. I've seen that happen to sicklers. Seen it. Don't do that. This is a serious, serious disease. It is a crippling disease. It is a deadly disease. And it is a true disease that truly does cause serious pain. We give out narcotics now for things we should not be giving them out, for most things that we should not be giving them out. But in this case, they need them. So think about me. If you see somebody discriminating against a sickler, and report it. Report them. And that includes physicians. It includes them. Okay. So anyway, I'm a little sensitive about that. I really am. Okay, so guys, proteins, and this is our biggest category as far as diversity goes, and we know what they're made of. We know that they do all kinds of things. They are also going to, another example would be insulin. So we have this entire category of hormones that are going to also be proteins. So some of our hormones are lipids, but some of our proteins are going to be, hormones based. Now, this last category, I want you all to know this last category is called nucleic acids. Nucleic acids, the monomers of nucleic acids are nucleotides. So a lot of students have a hard time with that terminology. But anyway, just so you know, the monomers of nucleic acids are nucleotides. And when you think about a nucleotide, let me tell you what they have. These are the common components of a nucleotide. They have a nitrogen base, they have a sugar, and they have one or more phosphate groups. So you'll know something would be a nucleotide if it had these components, okay? And I'm just going to talk about a couple of them. There's a whole bunch of them, but I want to talk about the major ones. And the first one I want to talk to you about is something called ATP. And y'all have heard of ATP. I need you to know what it stands for. It stands for adenosine triphosphate. And I know those of you in micro have this. It's like sort of is it just Kristen in my micro? Who else is in micro? Anybody else? It's Kristen. Okay, so I think we just had this. But anyway, so adenosine triphosphate is what ATP actually stands for. And this adenosine group, what this group is adenine that has the nitrogen base, and ribose is the sugar. How did I know this was the sugar? The OS. That's exactly right. The OS tells me that that's the sugar. So this is adenosine. And why do we call it triphosphate? Because it has 3 phosphate groups, like a little, and I call these like a little tail on a kite, right? Now here's what I want you all to know. This is actually called our energy molecule for our cells. The energy molecule for our cells, right? We're almost done with this. Are y'all hanging on? We'll take a little break in a minute, but y'all hanging on? All right. So this energy molecule, why it is an energy molecule is because of its structure. And I know y'all get sick of me saying structure dictates function, but I want you to pay attention to this little structure. look at this right here. This has a little tail of phosphates. And when this little diagram here it looks flat to you, but we know it's not. These are atoms of elements that are three-dimensional. And we know they have a relationship called a chemical bond. Is that right? And held within chemical bonds is energy, stored energy is held within chemical bonds. So like Julie and I, she's a phosphate and I'm this last little phosphate on this tail. Julie and I are having a relationship here. And if Julie tried to pull away from me, there's some energy in there, Julie? There's some energy, you feeling it? Okay, so there's some energy in here, and we do have it. Y'all can't feel it, but there's stored energy in here. The thing about this molecule, and it's kind of beautiful, the last little phosphate group will break off rather readily. But when it breaks off, it's going to give off energy, just like a stored battery that's charged. So here we're charged. Here we're giving off energy. The thing is, did I disappear? No. So guess what I can't, with a little energy put back in, guess what I can do? Recharge. So inside your cells, you have a ton of ADP, and you have phosphate group, ADP, these two adenosine diphosphate. And phosphate groups with a little energy, they'll what? Recharge the battery. But when you need the energy, they will break off and supply it like a charged battery. So what do we call ATP? A what? We call it an energy molecule because it acts like a what? A battery with full charge, has an ATP. Are you good with that? Now I want to show you something, and I want you to kind of remember this. Not kind of, I definitely want you to remember this. You guys, what did I tell you? What did I tell you C6H12O6 is? That's so awesome. And if I had 6 of these, what is that? 6 what? 6 oxygen molecules, didn't it? 6 oxygens. Okay, that's kind of cool. All right, now, if I were to tell you that inside of our cells, we can rearrange these molecules. Didn't you say we can do some things like that? We can do all kinds of things inside of our cells and end up with 6, what is that? Carbon dioxide, 6 carbon dioxide, and 6 what? 6 what? Okay, so here's what I want you to see. Did we lose anything? Do we still have 6 carbons on this side that we started with? Yes. Do we still have 12 hydrogens on this side? Yes. Yes. So we didn't lose anything. We just did some magic. All right, so here's what I want you to know. I want you to know that chemical equation. It's rare that I ever want you to know chemical equations, but I want you to know that one. And I want you to know that chemical equation is called aerobic respiration. Aerobic respiration. It is also sometimes called cellular respiration because what are the cells doing? Cellular respiration. It's a way that the cells are breathing, which means that the way that the cells are actually living and surviving, and it does take this. So here's what I want to tell you all about chemical equations. How many of you love chemistry and love chemical equations? And you remember that with the arrow, and sometimes the arrow can go the other way. Y'all remember all that? So you remember that. And hopefully you remember this, that chemistry is nothing unless you understand that in this equation, in this arrow is a story. And if you don't know the story of that, you can learn chemistry. So do you want me to tell you the story? Do you want me to tell you how you can go from 1 glucose molecule and 6 little oxygen, and what the story is that's going to get you to these? Sure. Okay. So you need a nightcap to go along with that story, right? But anyway, okay, no matter. But okay, I'm going to tell you that story because it's important that you actually know that story. So here we go. You ready? You ready? What did I tell you all this is? Look at y'all know my artistry already. I'm like, it's not even a very good drawing. But anyway, this is the nucleus of a cell, which holds the DNA. Okay. And this was the plasma membrane. And so, okay, so we've got a cell here. And I do want to tell you all the story of what's actually happening here. So you ready? The first thing is that glucose can come into the cell. It gets escorted into the cell. Y'all know that. What did y'all say is needed for glucose to come into the cell? So glucose gets escorted into the cell. And you know what? As soon as it gets into the cell, it splits. The molecule gets split. And when that molecule gets split, do you think it's going to take energy to split that molecule? It is. It is. This is actually called, let's see if I can do it, glycolysis. Lysis, lysis means to split. Glyce means what? Glucose, splitting glucose. And y'all said to do that, it would probably take a little energy. Is that right? And it does. It takes a couple of ATP molecules. It takes a couple of stored battery molecules to be used to split it. But you know what? It takes a couple, but you get 4 made on the back side. You get 4 made. So now we have 2 ATP being made. That's kind of cool as a product, right? Is that kind of cool? Is everybody with me so far? This is the first step. Okay. Now, let me tell you about the second step. And this second and third step are happening in organelles known as mitochondria. These mitochondria are not this big compared to the nucleus, but these are called mitochondria. Mitochondria, I'll just abbreviate that. Y'all know that, right? Mitochondria. These mitochondria are called the powerhouses of the cell because energy is going to be made here. So these second and third steps are actually happening here. And in the second step that's happening inside the mitochondria, we're going to get 2 more ATP made. So how many do we have now total? Just from glucose. Just from glucose. We have 4. Woohoo, we can have a party, right? Wrong, because our cells are really complex and our cells require a lot of battery reserve. That means they require a lot of what? But here's the beauty. If we can bring oxygen into this third step, which is really happening in what area? The mitochondria. We can end up getting 32 ATP more. So that's a total of how many? How many? 36 ATP. Are you kidding me? In this story, when these 2 reactants, these are called reactants on the left side of the equation, right? When these 2 reactants can come into a what? A cell, we can get what? 36 ATP. That's crazy. That's crazy. From 1 glucose molecule and 6 little tiny oxygen gas molecules, we can get 36 ATP. And at the same time, in this second step, what will be sent out of the cell? And in this step, this third step, what will be sent out? Water. So as long as we can get a glucose and 6 oxygen, we can put out a little innocuous gas like CO2 and some water. And in the process, in our story, we're getting what? We're getting 36 little batteries recharged. I would do anything to charge your phone batteries, admit it. So look, I mean, anything. You go sit in your car, admit it. How many were sitting in their car when power was out recharging your batteries? Thank you. Thank you for admitting it. Guess what? I did too. Because I always I let my guy, I'm not thinking until the power's out. And I think, oh, my cell's dead. My cell phone's dead. So anyway, I was doing the same thing. Guys, that's the story that's happening. You know, when we look at that equation, it looks so incredibly boring. But look at what's happening for that, right? That's chemistry. And what is that equation? Cellular respiration, also known as aerobic, because what must you have here? And if you looked at the oxygen, could you like sort of say that was the most important part? Because where did you end up getting the most energy? That third step in the mitochondria, right? So yeah, we can get a little bit of energy just from splitting glucose and sending it into this second step, the Krebs cycle. We can get a little bit of energy, but can we get enough? No. Close your nose and mouth. No, we can't, because your cells are going to start to do what without it? Die. We have to have charged batteries constantly. And this is how it's happening. This is the cleanest, quickest sort of way that it's happening. What is the energy molecule? What is the energy molecule? It's ATP. Do you know exactly what it stands for? Adenosine triphosphate. You guys, this is showing you this kind of thing. All the things. Now, this is just giving, this et cetera is huge, because it's any work that's happening inside the cell is needing what? ATP. Anything that's happening is needing that. Do you see why I want you to learn the glucose molecule first, and then you're building, so you're not having to do things from scratch building. This is the last thing of our notes for this part of chemistry. Y'all already know what DNA stands for. I had asked you to know that. And what I really want you to know about that is that's your entire recipe book for all of your proteins. Nobody ever stopped me when I was talking about the primary sequence of amino acids coming up and getting in a particular order. But what dictates that order is the DNA molecule. It holds, when I say it holds all the recipes for your traits, what I am saying is that it holds the recipe for which amino acid comes up and gets in what spot. This molecule does that. And did y'all tell me that's an important thing, which one is in what spot? Because if one is off, can you have such a devastating disease as sickle cell? If one is off, it can mean sometimes immediate death for the organism. That organism's not going to live. It can be immediately fatal. If one is off, it can just cause a change in a trait. If y'all look at diversities of eye tone and melanin color, that was because of changes, slight changes in recipes of traits that had happened that didn't adversely affect, just gave variability in our traits over time. We can actually clock back to when the first mutation happened. And I'll talk about mutations later, but the first mutation that happened that caused blue eyes, we know when it happened and know exactly when it happened. And the people who have blue eyes now are a little bit, we're all related, but they're a little bit more closely related than people without that, because we know when that mutation occurred. That's kind of cool, isn't it? Okay, so anyway, DNA holds all the recipes for all your traits. RNA, what I want you to know about RNA for right now is that it helps the DNA molecule carry out the recipes and cook them, if you will. There are different kinds of RNA, but you can think about RNA as holding individual recipes. So it assists DNA in carrying out the recipes for the trait. Does that make sense to you? For now. And that's fine. That's all I want you to know for now. All right. So guys, chemistry, pat yourself on the back. You are done with the biochemistry that you need. I mean, we'll add a few little things as we go, but pretty much that's it. If you feel really insecure about it, just go back and review it. We don't all have to get to the, to the finish line at the same time. So if you didn't do great today, no big deal. But go back and get it, right? Go back and get it. All right, so do you have any questions for me? Let me say this while the recording's going. It's for a few people who aren't here. Your second lab is actually going to be I have given you all on the visible body a couple of things, haven't I? And one of them was like medical terminology. Have y'all looked at that? Is everybody looking at that? Jojo. Yeah, thank you, Jojo. Yeah, so y'all are looking at those. So on the second lab quiz, I can use any of those terms that were on there and ask a question about them, can I? Y'all would know what they meant. That's fine. And then on the second thing that you had, it was directional terms, wasn't it? Prone, supine, they were just directional terms, weren't they? Proximal, distal. Would it be fair for me to ask you anything that you see on there? Would that be fair? It would, wouldn't it? Now I need to add something to that, and it's in your textbook. And here it is. This is for second lab, so y'all need to, today you have your quiz, your lab quiz on measurements in science right after the break. After the break, measurements in science? Okay. But today, what I also want you all to know that for your second lab quiz, which will be a week from today, that second lab quiz will be a week from today. In Atlas 1, I want you all to look, and you will see this page. Do you see this page of it says I wish I could read. It says regions, right? And it gives you a male and a female, and it gives you an anterior and a posterior aspect. Y'all see that? Y'all see this picture? Yes. All right, so from this picture, you all are to know everything on this picture. Okay, so what that means to you is this. Is everybody looking at somebody's book if you don't have it? I want y'all to do this now so y'all know and you won't have to know. So on the visible body, you're looking at two things, medical terminology, and you're looking at the directional terms. Is that right? Right. And in the book, you're looking at this picture that says figure, I think it's A.3, the adult female and male bodies, regions. Let's look at this for a second, and let me tell you how I'm going to ask questions. I'm going to tell you exactly what the questions will look like. You ready? I will say something like, the armpit is more accurately referred to as, and you will have to write in and spell correctly, the axillary region. Are you good? Or I might say this. I might say the carpal region is more commonly referred to as the, and what would you put in? All right, so look guys, anything that's on this page is fair. Learn them, okay? And I will give it, they will be filling in the blank exactly like the example I just told you. Okay? And we can play with it some more if you want to. This is not hard. This just requires time. Isn't that right? It's not hard, just time is all that is. But time's valuable, so start now. Because it will run out on you. Okay. This lab quiz, the lab quiz that will include this, plus those two things from visible bodies, that will be 1 week from today. Good? All right, now, I don't think I included, those of you who've gone to visible bodies, did I give you all that that little scavenger hunt thing? Did I link that to y'all? Did I did. That was actually just for fun, and nobody's considering it fun. And so anyway, people are like, oh, they're like panicking over this. So that, if I don't tell you out loud on the visible body what I linked as an assignment, are you going to have it as a test on the test quiz? No. And if you do, what would you tell me? You didn't tell us that we needed that. And guess what I'll do? I'll take it off. So study what I tell you to study, okay? Study and do more if you have time, but most people don't. Okay, so do you have any questions before I stop the recording?